continue now with the lectures on high-energy galactic gamma-ray sources. Perhaps you remember that in the last lecture we saw the different type of acceleration mechanisms for charged particles. We saw direct acceleration in huge electric fields in compact objects, and also diffusive acceleration mechanisms, either mediated by shocks or by turbulence or magnetic reconnection. And then also we have a look at the different type of interactions that relativistic particles can have with a variety of targets, matter fields, radiation fields, magnetic fields, and so on. So today I propose you to look at the thing itself, to study some concrete gamma ray sources in our galaxy. So let me start just reminding you the Fermi catalog of gamma ray sources. These are high energy gamma ray sources. This means gamma ray sources with energies above 100 MeV up to 100 GeV. So you remember from yesterday this image of the galactic plane with a lot of diffuse emission, and superposed to the diffuse emission you see some discrete sources. So we are going to pay attention to the discrete sources, but I would say also a few words about the passive sources, the targets, the passive targets for galactic cosmic rays. So I also yesterday presented you this pie chart. 61, almost 62% of the sources detected by Fermi are extragalactic, blazars. But among the galactic sources, we have supernova remnants, pulsar wind nebula, pulsars, globular clusters, binary systems, for instance, with a compact object, black hole, or a neutron star, or even binary systems formed by two massive stars. So today we are going to have a look at those sources. If we go to the detail of galactic sources in the catalog, we have all these identifications that you see here. We have 237 pulsars for which the pulsations in gamma rays were detected. So there is no doubt that these sources are pulsars. We see the pulsations. And then we have another 3 or 4 more for which there is no pulsations, but this could be because of this issue we were discussing yesterday of the alignment between the magnetic momentum of the pulsar and the rotation axis. And then we have a lot of supernova remnants. 24 of them are extended, so the morphology has been determined, and so they are firmly identified. And there are other 16 supernova remnants that are not resolved, but are positionally coincident with the radio and X-ray counterparts of these sources. So we are pretty sure that these are also supernova remnants. Then we have many pulsar wind nebulae. 15 of them are extended, so they are resolved by Fermi. And then we have a large number of associations where it's not clear whether a supernova remnant or the pulsar inside the supernova remnant is producing the gamma rays we are observing. So these are composite sources. Then we have globular cluster, about 30. And globular clusters are clusters of stars, very old, that are orbiting around our galaxy. And 30 of them have been detected by Fermi. We have a number of high-mass X-ray binaries. X-ray binaries have a compact object and a massive donor star that transfer mass to the compact object. We will study these objects in a while. Then we have a 3 star-forming region, open clusters. These are regions of star formation, active star formation on the galactic plane in our galaxy, with plenty of massive stars, winds, and also supernova remnants. We have some low mass X-ray binaries. Here the donor star is an older main sequence star, like the Sun, for instance, and the transfer of mass from the star to the compact object occurs by overflowing the Roche lobe of the system. And Fermi also detected in this catalog, in the 4th catalog, 1 novae. These are explosions, thermonuclear explosions on the surface of white dwarf stars. And then we have a huge number, more than 1,000, sources that are not identified. So there's a lot of work ahead of us trying to identify these sources. If we go to higher energies, then we have fewer sources. This is the Fermi sky above 50 giga-electron volt. Here, most of the sources, once again, are extragalactic, 75% of them. And we have 11% of identified galactic sources, more or less the same types, pulsar wind nebula, some binary systems, and then supernova remnants, mostly in interaction with molecular clouds, and also microquasars and even a very massive star that we will discuss in detail later. And if we go to higher energies, to the HESS Galactic Plane Survey, we have, as you see, a lot of sources, discrete sources. Some of them are resolved by HESS. And this is the distribution of the sources in the sky. You see a strong concentration of high-energy sources on the galactic plane. And this includes a lot of pulsar wind nebula that write a lot at these TeV energies, and some supernova remnants interacting with molecular clouds, shell supernova remnants, binary systems, and star-forming regions. Okay. So, talking generally, these galactic sources can be separated in 2 great groups: passive sources and active sources. What is a passive source? Is a source that is not accelerating itself, particles up to relativistic energies. It's just a passive target for particles that are accelerated elsewhere. And these passive sources are in 2 flavors. They can be diffuse sources, like, for instance, the diffuse emission that we have seen in the Fermi all-sky map, or the sources could be discrete, passive discrete sources, like a molecular cloud that is irradiated by cosmic rays that are accelerated in a nearby source. And then we have the active sources. These are perhaps the most interesting type of sources. These are sources where both electrons and protons can be accelerated locally up to very, very high energies. So in principle, these particles, while being accelerated, they have losses, and these losses can be in the gamma ray band, so we can detect these sources if there is a suitable target in the source for the production of the gamma rays. Let me say just a few words about the passive sources. You remember that yesterday I introduced the gamma ray emissivity of a given source. Now allow me to introduce the specific gamma ray emissivity. It's just the gamma ray emissivity we saw yesterday divided by the number density of particles in the source. So the flux of a given source located at the distance d that radiates isotropically, hence the 4p that you see here, can be simply obtained integrating the density of the target, the passive target, with the local emissivity, specific emissivity at the source. So if we know the density, because, for instance, we have radio observations, for instance, in the H1 line at 21 centimeters of wavelength, so we can sense the number of hydrogen atoms there, and we have an idea of the size of the source, we can infer this density. But what about the specific emissivity? Well, the idea is that the specific emissivity, divided the specific emissivity in the local neighborhood of the sun, is of the order of the ratio of the cosmic ray density in the source divided by the local, in our environment, of cosmic rays. And this number is called Ks, S for the source. So the specific emissivity is nothing else than the product of this number, the enhancement of cosmic rays in the source with respect to the local cosmic ray density, times the local cosmic ray density, times the local emissivity. So we can put all this in terms of the local emissivity, and if the integration of the number density of the target give us a total mass m of the cloud, because normally these are molecular clouds in the outer space, and the cloud is mostly formed by hydrogen, so I am dividing here by the mass of the proton. We have this very simple expression to get the flux, the gamma ray flux at energies about 100 MeV due to proton-proton interactions in the source. If we put this in convenient units, we have this expression here that is valid by for energies above 100 MeV. So using this, you can get a very rough estimate of what would be the emissivity, the flux from the source. Actually, this use the other way around. You measure the flux, and you determine, using radio astronomical tools, what is the mass of your target, and then you determine also the distance through different methods, so you can infer what is the cosmic ray enhancement in your target. So if you have different targets at different distances that are irradiated by some hidden source of cosmic rays, you can determine how this number is changing with the distance to the source, if you can measure the gamma ray flux from each of these clouds. And from that, you can solve the inverse problem of determining which is the diffusion coefficient in the interstellar medium. So this is very useful. Well, let's see some examples. This, for instance, is a dark cloud. You see why it is dark. You see nothing through it. It's a field plenty of stars, but the cloud absorbs the light from the clouds. This is Barnard cloud. It's very nearby, so there are no stars between us and the cloud. So you see here the cloud. This is in the optical regime, but if this is irradiated by cosmic rays, then this cloud could bright at gamma rays. It has not been detected so far, just because the sensitivity of our instruments is not well enough. And this is another region that in our galaxy is plenty of gas. It offers a lot of clouds and passive targets for cosmic rays, and we have there several different types of accelerators of cosmic rays. This is, of course, the galactic center region. So here is Sagittarius A star. So the supermassive black hole in our galaxy is located here, inside here. This famous image obtained by the Event Horizon Telescope is an image of this region in the millimeter wavelengths. This instead is a map obtained with a Meerkat interferometric array at 1.2 gigahertz. And here you can see a lot of different things, giant molecular clouds here, and also you see X-ray binaries, you see different type of objects. There are microquasars. You remember the great annihilator that I mentioned the last lecture is also here in this area. There are several microquasars, pulsars, and different things that are orbiting, many stars also, and clouds that are orbiting around the central black hole. So this is the center of gravity of our galaxy. So it's plenty of things. And when we look at this region, not in radio, but in gamma rays, we see something like this. The color is the map, the gamma ray map obtained by Hess of the galactic center region. And superposed, you see as contour lines the distribution of matter, in this case CS matter. And this is an indication of the concentration of gas, and you can see that the brightest parts of the region in gamma rays are also coincident with the highest concentrations of gas. You can see that better in this figure here, that essentially is the same, but here you see the profile of the gas. So you see the molecular clouds here as these peaks, and you see that these peaks are coincident with the excesses in gamma rays. So what we are seeing here, what we are seeing is a number of clouds, huge concentrations of matter that are passive targets for cosmic rays that are accelerated somewhere, somehow in the galactic center region, by the galactic center black hole, or by nearby microquasars, or by nearby supernova remnants, we do not know. It's a very complex region, so it's very difficult to disentangle the different contributions. Okay, enough about passive sources. Now let's focus on to the active ones. So the most common type of active sources at high energy and very high energy gamma rays are these: supernova remnants, the remains of exploded stars, then star-forming regions, the cradles of stars in our galaxy, open clusters, plenty of stars in the center. There is ongoing star formation there, and these are very massive stars, O stars, B stars, stars that are very hot with very powerful winds. So the winds creates a cavity, a bubble that favors the formation of gamma ray sources, as we will discuss later. Then we have some pulsars that are non-accreting, so these pulsars produce radiation in gamma rays by the mechanism that we were discussing yesterday. You remember these pair cascades in the polar cap of the pulsars. So this produces an ejection of an electron-positron wind and gamma rays from the polar cap. we have novae that are binary systems where we have a star and we have a white dwarf, and the star donates mass to the white dwarf. And at some point, there will be a thermonuclear explosion on the surface of the white dwarf. And the white dwarf is not destroyed by this explosion, as it is the case in a supernova type 1a. But the systems are recurrent. They can repeat these thermonuclear explosions from time to time. Then we have a system with colliding winds. For instance, systems formed by a pulsar with a wind with a massive star that also has a wind. Or we could have two massive stars, each one with a very powerful wind, and these winds collide, form strong shock, and particles are accelerated in this shock. We will see some famous examples in a moment. And then you have the microquasars. Microquasars are scaled-down version of extragalactic quasars, and I will discuss these monsters in detail later. So let's start with the supernova remnants. These are the remains of stars that exploded, massive stars. So the compact remnant used to be a pulsar. And then we have an ejecta, that is the gas expelled by the explosion. And all the dynamics of the supernova remnant is determined by the initial energy release, the mass of the ejecta, and the medium where this ejecta propagates. So in general, we have 4 phases in the life of a supernova remnant. The first phase is the free expansion. At the beginning, the ejecta just move freely because there is no essential opposition to the motion of the ejecta. So it expands without deceleration. So the size of the remnant is proportional to time. And then after a while, the shock that the explosion created in the interstellar medium sweeps matter in an amount enough as to modify the dynamics of the ejecta. This occurs when the mass of the ejecta is of the order of the mass of the swept up material of the interstellar medium. In that case, the dynamics starts to be affected. Now the evolution of the size of the supernova remnant goes with the time to 5. And in this case, the main losses are adiabatic losses. For that reason, this is called the adiabatic or the Sedov phase of the expansion of the supernova. It lasts for around 30 to 40,000 years. This first phase lasts just a few thousand years. These two phases are very prone to accelerate particles up to relativistic energies. And then we enter in the radiative phase. Here, the post-shock region becomes very hot, so it emits a lot of thermal radiation, and thermal radiation quench the Fermi acceleration process. Why? Because you remember that for Fermi acceleration, we need to have these magnetic inhomogeneities on both sides of the shock, so the particles can be scattered across the shock front. So if in the post-shock region we have a lot of radiation, this means that the entropy will increase significantly. You remember that the entropy, the variation in the entropy, is just the exchange of of heat divided by the temperature at which that occur. So if in this phase the entropy increases, this means that in the post-shock region everything is more homogeneous, because high entropy means high homogeneity, and this destroys these dispersion centers that are necessary for the scattering of the charged particles. So the mechanism stops being efficient. So we do not expect significant particle acceleration in this phase. And finally, we have the disappearance phase of the supernova remnant, when the expansion velocity decelerates through the velocity of the random motions in the interstellar medium. So just the remnant disappears in the interstellar medium. In the most interesting phases, these two phases, we have a forward shock, we have the ejecta, and we have also a reverse shock that moves inwards the supernova remnant. Both shocks can be adequate for the acceleration of particles. Okay, so this is here you can see a summary of the time evolution of a supernova remnant. Here we have the size of the remnant versus the age of the remnant. So this is the free expansion phase, this is the adiabatic phase, this is the radiative phase, and this is the final dissipation phase. And here you have indicated the typical temperature of each phase and the velocity of the shocks in these phases. So you see that for the Sedov phase, the adiabatic phase, we have velocities that are of the order of 10,000 kilometers per second. So this means that Fermi type 1 acceleration mechanism could be quite efficient. Okay, this is the scheme of the unshocked ejecta, then the shock ejecta, and this is the shock interstellar medium. This is a density profile of a supernova that still contains a pulsar inside. So the pulsar produces this wind we have mentioned, and this wind creates a bubble, an almost empty region at the core of the supernova remnant. And then we have the peak of the ejecta in the density, then the cold ejecta, the reverse shock, and the forward shock. And these are some images of supernova remnants, the same actually supernova remnant, sorry. Observe at different wavelength. For instance, this is at 4.4 gigahertz in radio, and this is in X-rays between 4 to 6 kilo electron volts, continuum emission. And this is line emission. This is silicium, the silicium line. And here you have a microwave image of a shell-type supernova remnant, the same one. And here you have another sub-millimeter image. So you see the morphology can be quite different depending on the wavelength that you are using to observe the remnant. Okay. This is the full list of supernova remnants that are firmly identified with gamma ray sources and in the different gamma ray bands. So here you have the GV band, essentially Fermi, the TV band, and finally the PV band. These are the three supernova remnants that are identified by lasso experiments. We heard from Socha San about these three remnants. And then at TV energies, we have many of them. These are essentially the Hess detections. And we have many of them at GV energies. Some of them are quite famous, historical remnants that the explosion, where the explosion of the star was observed in historical times. For instance, Kepler supernova remnant. Also, we have Cygnus loop, Gamma Cygni, IC43, very famous one, Monoceros loop, Papis A, Villa Junior, that was discovered just 25 years ago. And this another one that is quite famous because it has been extensively studied is RxJ 1713-39. Okay, so let's see some of these supernova remnants in gamma rays with a bit more detail. This is the supernova 1006. It's called like that because it corresponds to an explosion that was observed at that year, 1006. So it's a supernova with 1,000 years of age. It was. It is still in the free expansion phase. There is no pulsar observed. Perhaps the pulsar escaped, or perhaps this was the result of a supernova type 1, where the white dwarf was completely destroyed by the explosion and no solid remnant was left behind. And this is what is observed by Chandra in X-rays with high resolution. You see that the morphology of the remnants is perfectly resolved. And you see that there are some more bright parts, filaments, on this northeast and southwest edges of the shell of the supernova remnant. And this is interpreted as synchrotron radiation produced by multi-TeV electrons. How do we know the energy of the electron? Well, because if this is synchrotron radiation and these strips are very thin, then the cooling time of the electrons should be quite fast. So if we have some idea of what is the magnitude of the magnetic field, using some of the formula I showed you yesterday, you can easily calculate what is the energy of the electrons. And this gives you multi-TeV energies. So those very same electrons can upscatter CMB photons producing gamma rays. And actually we observe the gamma rays. This is the Hess map superposed with the Chandra map, precisely where the most energetic electrons are located. So in this part of the remnant, acceleration seems to be particularly efficient, at least for electrons. And we have associated gamma ray sources that are the result of upscattering of CMB photons by this very same population of electrons that are producing the synchrotron radiation observed by Chandra. And this is the spectral energy distribution, and a very simple model where this is the synchrotron peak and this is the inverse quantum peak on the CMB. Okay, very simple case. We have morphological match. Actually, is a quite simple inverse problem to solve. Well, this is another case that is not too much complicated to solve. This is the famous Tycho supernova. It's called Tycho because it was discovered by Tycho. And in this case, we also have these trips in the X-rays. Again, this is a Chandra image of the Tycho supernova remnant. It's quite young, obviously. And you have the strips, and these strips, once again, indicates us that electrons are being effectively accelerated there. But we have here another ingredient. If we look at this source using radio telescopes, we see that there is a huge molecular cloud just on the side of the supernova remnant. This is the supernova remnant in X-rays, so this image here. And we have this huge cloud that is interacting with this part of the supernova remnant. So the situation is something like this. We have the supernova remnant, we have the cloud here, and then if in addition to these electrons, protons are being accelerated there, these protons will interact with the matter from the cloud, producing significant gamma radiation through pion decays, neutral pion decays. And actually, we can make a quite good fit of the source using synchrotron radiation for the X-rays, for this image, and also we can reproduce the radio images of the supernova remnant. But then at the GV energies, up to TV energies, we have a hard spectrum that can be well fitted by proton-proton interactions. And the inverse Compton component that corresponds to these electrons that are producing this synchrotron radiation is this small component here. So essentially, the high energy emission is dominated by hadronic interactions in this case. And this curve here is the relativistic bremsstrahlung produced by the electrons in the matter of the cloud. So we see that in this case, things are not so easy as in the previous case for the analysis. We have several components contributing to the high energy emission, but there is a clearly dominant one that is the hadronic one. So this is one of the first supernova remnants that allow us to claim, okay, supernova remnants are good contributors to the TV cosmic ray spectrum in the galaxy, as was proposed half a century ago by Ginsburg, Sirovatsky, and independently by Shklovsky. Okay, but there are much more complex cases, and one of them is this remnant, RxJ1713-39. It's an ugly name. I don't understand why they do not call it Peter or something like that. Okay. These are the images obtained by Hess. This is for energies above 250 giga-electron volts, and this is for energies above 2 TeV, tera-electron volts. So you see that it's a kind of a shell type. The interior is empty. You see the shell clearly. And the problem is that when you observe what is going on at other wavelengths, for instance, with radio telescopes, and you determine the content in this region of neutral hydrogen or molecular hydrogen, then things become very messy. You see a lot of material around this supernova remnant. So different parts of the supernova remnant seems to be interacting with different amounts of matter. And this makes the determination of the different contributions quite difficult. This is also observed by Chandra at other wavelengths and by Susaku at X-rays. So this is just an attempt to fit the entire source. And it's very difficult. You see that the synchrotron radiation, if you try to match the Susaku data, then you are missing the radio data from the Australia Telescope Compact Array. And here in gamma rays, you have a pion zero component, but also you need an inverse Compton component and also a bremsstrahlung component in order to get something more or less adequate. But nevertheless, it's very difficult to match the entire supernova remnant just with a single populations of particles. So Hess studied this source, just decomposing the image in, as you see here, almost 30 different pieces, and it was determined in each one of these pieces which was the most relevant radiative processes. And the result, of course, is quite complex, but in average, we found that about 67 plus minus 8% of the radiation at high energies come from hadronic processes on average on all these regions you see here. And 33 plus minus 8% seems to come from leptonic, inverse Compton interactions. So the final fit is quite complex, and you need to do it piece by piece, and not you cannot fit the entire source with a single population of particles. So this example shows how difficult sometimes is to understand the data we are obtaining here on Earth, because there are many, many different components in a very complex environment that are contributing to what we see. Okay, now let's move to the Crab Nebula. The Crab Nebula is a supernova remnant associated with the Crab pulsar. This is perhaps the most famous supernova remnant in the galaxy. It was, the explosion was observed by the Chinese in the year 1054, and it's a very, very young system. Here you can see the Crab Nebula at all different wavelengths: radio, infrared, optical, ultraviolet, X-rays. I show you a movie made by Chandra about the X-ray emission from the nebula. This is the interior of the nebula, and gamma rays. This was, during many, many years, the standard candle for gamma ray astronomy. So to the point that sometimes the Crab unit is used as a measurement of the intensity of a gamma ray source. And some basic data about this supernova remnant. The expansion velocity of the shell seems to be of the order of 1,500 kilometers per second now. And the size of the source, the major axis of the source, is of the order of 4 parsecs. So still is quite compact because it's very young and is still at the end of the free expansion phase. The mass of the ejecta is large, quite large, of the order of almost 5 solar masses. So you see all that mass in these filaments that form the ejecta, that are very clear in the optical. Okay. And in the center of the Crab Nebula, we have the Crab pulsar. This is a young pulsar, so it rotates very fast with a period of 33 milliseconds, so 33 spins in a millisecond. And then it is located at 2.2 kiloparsecs from us, and the total power emitted by the pulsar is at the level of 10 to the 30 H per second. It's the most powerful pulsar we know in the galaxy. There's a lot of energy. Remember that the bolometric luminosity of the sun is 10 to the 33 H per second. Okay, and this is the periodic emission of the pulsar. So you see the peaks, and they are very clean peaks. And this pulsar ejects a lot of electron-positron pairs that creates this this pulsar wind nebulae that is inside the supernova remnant. So it's inside here. This is in X-ray, but well, in optical wavelengths we do not see it, but it's inside here and creates a bubble, a cavity inside the pulsar with very low density. Well, what about the spectral energy distribution from radio up to high energy gamma rays? Well, this is one of the best observed sources in the galaxy. So we have a lot of data from radio, as you see here. Then we have the X-rays, and then we have the gamma rays from high energy up to very high energy gamma rays. So it is observed even beyond 10 tera electron volts in gamma rays, up to almost 100 tera electron volts. So it seems to be a pevatron. The particles that are producing the most energetic photons in this source should have energies of around 1 PeV. So the spectrum seems to be quite clean, actually. It's not a messy spectrum as in the previous supernova remnant that I show you. And that is because this is in a clean environment, that there is no major cloud superposed with this object. So all this part of the spectrum clearly is synchrotron radiation by these extremely energetic electrons. This synchrotron radiation can reach up to almost 1 MeV. And then we have this component, this second peak in the spectral energy distribution, that is inverse Compton radiation. But this inverse Compton radiation is contributed by a different component, not just a single component. Why? Because we have different ambient photon fields acting as target of the quite energetic electrons. For instance, here you have, well, these are two examples of fitting of this part of the spectrum. You have a component that is the synchrotron self-Compton radiation. So inverse Compton upscattering of the synchrotron photons, of these very same photons by the very same population of electrons that produce these photons. So this is this line here, so it's the major contribution. Then you have the nearby infrared field that is omnipresent in the galaxy, is produced by the dust in the galaxy. So this contribution here is a minor contribution. Then we have the far infrared field, that is this one here, that is much more important. And finally, we have the CMB, that is this one here, and that helps to shape the end of the spectrum. So you see that it's not so simple as just to take a single photon field, but you need a combination of them to get this excellent fit. Okay. Now there is something extremely strange about this system that was discovered almost 15 years ago. I mentioned that the CLAF was considered a candle, a standard source, a completely non-variable source because it's extended, remember, 4 parsecs, so it cannot change on short time scales. Nevertheless, on April 2011, this was observed. This is the normal CLAF. This is in gamma rays, as seen by Agile, the Italian gamma ray satellite. And here you have a nearby pulsar, Geminga, that also is a gamma ray pulsar that is detected by Agile. So you see that it's even brighter than the CLAF at this band. This is the MEV, multi-MEV band. But then suddenly, in just one day, the intensity of the crab increases by a factor of several. How that is possible if the size of the source is 4 parsecs? So it's impossible. So people were perplexed. And they were using this source as a standard calibrator. So then they realized that sometimes they have, in the past, attributed rapid variability to some blazer, for instance, using the crab as a standard source, and then they checked in the light curve of the crab, and they realized that was the crab actually what was varying, not the blazer, the extragalactic source. So what is going on? So these are some examples. When they discovered, this is the standard crab in normal state, and they discovered this extreme flare. So you see that the flux increases in a factor of many. They went back in time, checking the historical series, time series, and they found also other not so intense flares, like this one and this one. Well, for instance, in this one, the flux doubles on a time scale of 1 day or something like that. How that is possible? Well, people were perplexed. I was perplexed because I was working on this. And this is the major flare in 2011, just in a great detail. So you see that the source is quiet, and suddenly we have this emission here, an increase of factor of several, and then we have this huge flare that lasts a few days, 4 days, from here to here. And then it becomes normal again. So how that is possible for a source that is 4 parsecs in size? Well, there is an additional problem, and that problem is that this flare implied a violation of the Compton, the synchrotron limit for ideal magnetohydrodynamics. What is this? If you want to accelerate a charge, then in ideal magnetohydrodynamics, we need to accelerate it with some electric field E. So the force that accelerates the charge is the value of the charge times the electric field. But then the accelerated charge will produce radiation, as any accelerated charge, and the synchrotron radiation, and this is the value of the synchrotron radiation. You remember this formula because I presented it yesterday. So the maximum energy that a particle can have, if we take into account the back reaction force of the radiation, is obtained just equating these two equations. And we get this maximum Lorentz factor. Now, in ideal magnetohydrodynamics, you have the value of the electric field divided by the value of the magnetic field should be less than 1. Then this imposes a critical energy that is of the order of more or less 160 MeV. This is why if your source is accelerating particles in ideal magnetohydrodynamical regime, you could not have in your system synchrotron radiation with energy above 160 MeV. That is the absolute limit. Now, remember this number, 160 MeV. What happened with this flare that I show you in the graph? This is the cutoff of the spectrum, the synchrotron spectrum. So you can see that here you have the energy here, and here's the energy, and MeV. So 10 to the 3 MeV is 1 giga electron volts, 10 times more than the maximum possible limit for synchrotron radiation. But this is synchrotron radiation. It's just a continuation of the previous spectrum. And here you have the cutoff at 1 GeV, and again, and again, and again, in different days. So the cutoff, it's well beyond the synchrotron limit. How is that possible? But the only possible answer is that in the system, for a short lapse of time, ideal magneto-hydrodynamics was not occurring. There was a violation of this situation. So this indicates that the source should have been magnetically dominated in that period. So this is a spectral energy distribution where I have added the flare. So you see the synchrotron radiation, the usual one that is produced by this whole supernova remnant, and then you have this tremendous flare here that is a continuation of the synchrotron radiation, but now in clear violation of the the synchrotron limit. And then you have the standard inverse Compton radiation. So, in addition, there were no obvious counterparts in radio, infrared, optical, X-ray, or TV energies. So this appears only at MEV, GV energies. So what is going on? Well, the idea is that the responsible for this is this pulsar that we have inside the supernova remnant. This pulsar produces strong wind, as I mentioned. The magnetic field, you remember that there are open field lines. The system is rotating, so these magnetic field lines start to twist in this way. The pulsar is here, and these are the twisted magnetic field lines, and the particles that are ejected by the pulsar move along the magnetic field lines, force-free configuration. But sooner or later, the coherence is destroyed and turbulence emerges. So we have magnetic reconnection, and these magnetic reconnection events accelerate particles beyond the ideal limit of magneto-hydrodynamics. And if the reconnection event points to you, you will be a strong and very quick flare of synchrotron radiation by the electrons that are accelerated. These are simulations of how the regime changes as when you get away from the pulsar. So you see that turbulence starts to appear, and here you have these reconnection events. Okay, and if you calculate the spectrum of the particles under this regime with magnetic reconnection, then you have particles with energies that go well beyond the radiation back reaction limit that we saw a moment ago, and these particles, this tail here, can produce this radiation that goes beyond the limit for synchrotron radiation, and this explains the flare. So the situation is something like this. We have the supernova remnant that produces the standard radio, infrared, optical, X-ray, and gamma ray emission that we have modeled. And then in the middle we have the pulsar with a pulsar wind. There is a region, the inner region, that is unshocked, but at some distance the turbulence and the shock produce magnetic reconnection, and if you are here, magnetic reconnection can direct a beam of synchrotron radiation in your direction, and this is the flare you have observed in gamma rays. So this was quite a surprise when it appeared, and it has been observed many times since then. Of course, the crab is not the only pulsar wind nebula inside a supernova remnant. I mentioned that there's something like 70 other cases known in the galaxy. None of them is as extreme as the crab, but in some cases there are some very interesting phenomena. And the pulsars sometimes are born with a proper velocity that could be very high, for instance, up to 500 kilometers per second. This is because of the kick of the original supernova explosion that could be asymmetric, and then the pulsar can be expelled from the center of the supernova remnant. So this is a situation like in the crab, and this is a situation where a pulsar is just ejected, escape from the supernova remnant, and then it propagates, it moves through the interstellar medium, but the pulsar still ejects this wind, and this particle wind forms like a cometary tail around the pulsar. This is the Vela pulsar. You see that the pulsar is here, and then we have this cometary tail, and we have the gamma rays seen in this case by Hess, I think, coming from the tail. So this is the population of relativistic particles ejected by the pulsar, upscattering ambient radiation. And these are other examples that include Geminga. So you see an extended region of gamma ray emission that goes beyond the pulsar. So it's not a point-like source, and this emission is elongated, indicating a proper motion. Okay. And these traveling pulsars in the galaxy have many interesting features. For instance, look at Geminga. This is Geminga in X-rays. Look at the strange morphology. The pulsar is here. So the idea is we have the pulsar, the wind that the pulsar produces. It moves through the interstellar medium, and then a bob shock is formed because of the interaction of the wind of the pulsar with the ambient medium. The pulsar moves at supersonic speed in the medium. And since the pulsar also ejects to jets, then these jets are deviated, are bent by the interaction with the medium, producing these strange arcs that we can observe at X-rays. This is synchrotron radiation produced by the electrons that are being ejected by the pulsar. And this is another example of a cometary tail in X-rays by a pulsar. And this is another interesting phenomenon. Here you have the pulsar, and this is the cometary tail, and synchrotron radiation. But then we have this filament. You see that some filament that expels somehow from the pulsar, and in the transverse direction to the motion of the pulsar. And it's not deformed like the jets, like these ones here. It's just a straight line. How that is possible? Well, the idea is that in the interstellar medium, there are magnetic field, large-scale magnetic fields that can serve as a path for particles escaping from the pulsar. So the particles just escape through this large-scale galactic magnetic field. So this pulsar also can serve as a kind of probe to investigate the large-scale magnetic field structures in our galaxy. You remember when I show you the image of the galactic center, there was some arcs, some very strange filaments. What are these filaments? Those filaments are non-thermal, synchrotron radiation, so probably they are more or less the same like this one. They are filaments that are conducting electron-positron pairs that are captured in this rich region that is the galactic center. So there is, as you see, a very complex phenomenology associated with these young traveling pulsars. Okay, now let me say a few words about colliding wind binaries. Colliding wind binaries are systems, binary systems, formed by two stars, we have two massive stars. Each star has a powerful wind. See? This wind is produced by radiation pressure. Some of them are driven by lines, so some molecules absorb lines, the radiation transfer momentum to these atoms, and the atoms then put in motion the gas around the star, the atmosphere of the star. So a very powerful wind is produced. The mass loss rate in these winds could be huge, 10 to the 5, to 10 to the minus 5, for instance, solar masses per year. This means that in 1 million years, the star is losing 10 solar masses in the wind. So imagine the power of these winds. So if we have a binary system formed by two of these powerful stars, the winds will collide at some point in between. And then a system of shocks will be formed. We will have a contact discontinuity, and we will have reverse shocks that will move in the winds of the star. If these shocks are adiabatic, they can accelerate particles by Fermi first-order mechanism, and then these things will be bright in synchrotron radiation, also perhaps in gamma rays. So these are some simulations. For instance, here you have a very massive star and a less massive star orbiting around the center of mass, and the two winds are interacting. And you see that the interaction is quite complex because we have the Coriolis force, you have this cometary tail around the less massive star, and we have this complex boundary layer that is subject to different type of instabilities, Rayleigh-Taylor instability, mostly in this part, and then Kelvin-Helmholtz instability in the region where the flows moves with different velocities, as it is shown in this other simulation. Well, what are the examples we know in the galaxy of these systems that produce gamma rays? The most famous one is Eta Carina. Eta Carina is one of the most massive stars in our galaxy. Actually, it's a binary system. The most massive star has 90 solar masses, so it's huge. It's actually a luminous blue variable. It's a star that is very close to explode. So because of the mass of this star, we expect not a supernova explosion, but we expect a direct collapse to a black hole. And that is what is called a gamma ray burst. So this star will be the next gamma ray burst that will be produced in the galaxy. Hopefully the jet will not point in the direction of the Earth, because that could be dangerous. There are some interesting papers that have investigated what happened if the jet of a gamma ray burst produced in our galaxy impacts on the Earth atmosphere, and it's not nice. So let's expect that the jet will point in a different direction, or the star will collapse in a few hundred years. Okay, and this system is located in a very complex region. In the 19th century, there was a huge explosion in this star. The star expelled the outer atmosphere, creating this spectacular image that is called the homunculus. This is in an image from the Hubble Space Telescope. The binary system is in here, so we do not see the stars directly. We see the homunculus. By the way, the homunculus was discovered by the Argentine physics and astronomer Ernesto Gaviola. Gaviola was one of the most brilliant Argentine scientists. He was director of the Observatory of Córdoba, but previously he got his PhD with Planck in Germany and went to the United States with a reference letter by Albert Einstein, and he was the person that designed the technique to polish the mirror of the Mount Palomar telescope, 5-meter dish. So he became back to Argentina, started a group of discussion physics. Guido Beck, Giambiaschi, Bolini, Mario Bunge, all of them were formed around Gaviola. Not Guido Beck, because Guido Beck was older, but he promoted a lot of activity, and he was the director of Observatory of Córdoba. As it's usually the case in Argentina, now he is completely forgotten. Nobody cares about his contributions that are spectacular. And one of them was the first works on this system. Now, we can see through this this cloud in gamma rays. So this is the image of the central source by integral satellite, and this is the image of the source by Fermi. The source is not resolved at high energies. But the configuration is expected to be something like this. We have the more massive star, Eta Carina, here, and then we have the companion. That is a Wolf-Rayet star, also a very massive star, orbiting around the center of mass. So we have the collision of both winds and particle acceleration in the colliding wind region. So here you have some simulations made by Atsuo Okazaki of Eta Carina. This is the Eta Carina, the most massive star, and the small star you see here is the companion, the Wolf-Rayet star, and you see the complexity of the wind interactions with all the instabilities and all the details on the simulation. These are big simulation, particle and cell simulations that track millions of particles. The Chukawa Center for Computing Astrophysics was used to make these simulations. And here you have the basic information about this amazing system. So, for instance, the period, the orbiting period is of about 2,000 days. The last conjunction, I think, was a few years ago. And the inclination angle is 45 degrees. The eccentricity is high, is 0.9. And then the mass of the primary star is 90, as I mentioned, solar masses, and for the secondary star is 30 solar masses. And pay attention to this number. The total mass for loss from Eta Carina is 10 to the -3 solar masses per year. So in just 1,000 years, it ejects in the wind a solar mass. It's amazing. And the other star is also quite powerful, 10 to the -5 solar masses per year. Of course, the wind of the more massive star is slower because it's a lot of mass to put in motion, 500 kilometers per second, and the secondary wind has several thousand kilometers per second. So what happened with the high energy spectrum? Well, it's very different along the orbit. During the periastron, you have high energy emission that you can see here, this tail that can reach high energies. And during the apastron, you only have this component here. This component here is interpreted as inverse Compton radiation from the stellar photons. But during the periastron, there is a lot of matter, ambient matter, available. So proton interactions become important. Pions are produced, and we get a hadronic component as well. So if we look at the entire spectral energy distribution, we have something like that. This is the synchrotron radiation. This is the inverse Compton peak, and here we have the hadronic component. This is the thermal emission that is not modeled in this calculation. And this is the evolution with time. You see different periods. So the last one was in 2020, and the next one will be next year. Okay. And well, there is another of these systems in the galaxy is Gamma Velorum, but Gamma Velorum is not so spectacular. We can detect it in gamma rays just because it's extremely nearby. It's just 3 parsecs away from us, so it's the nearest colliding wave binary. And then there are other candidates, very powerful systems that are detected as non-thermal radio sources, like WR147, 46, and the famous Wolf-Rayet's 140. This is the evolution of the colliding wind front in the binary system as seen by synchrotron radiation measured by the Australia Telescope Compact Array. And also we have this other system in Cygnus OB2 is the system number 5 in this stellar association. So all these candidates were predicted almost 25 years ago by Paula Benaglia and myself. So this is not new stuff, but only recently these systems were detected as predicted in gamma rays. Okay, and since the orbit is quite elliptic in many of the systems, not gamma rays, the gamma rays are not seen all around the orbit. They are just some locations in the orbit where the gamma ray emission is favored. And then we have similar systems, but that can reach higher energies among the so-called gamma ray binaries. Gamma ray binaries are systems formed by a pulsar with a powerful relativistic wind and a massive star. It's a combination of what we have seen so far. And this is the list of these systems in our galaxy. In several of them, the pulsar has been already detected through pulsations, but in others, there remains the identification to be done. So there are some extremely famous ones, like PSR 1259-63. This system was postulated as a potential gamma ray source by Marco Tavani a long time ago in the 90s. And then we have LS 161303. I was one of the first to work on this source predicting gamma ray emission. And then you have this system, LS 5039, that was at the beginning thought to be a microquasar, but now is suspected to be a gamma ray system that was studied by the Barcelona group since the early this century. And well, this is a simulation of one of these, of one of these systems, also by Atsuo Okazaki, and you see a similar configuration as in the case of the colliding wind binaries. But now the wind from the pulsar, this is the pulsar, is relativistic. So the velocities of the shocks in the wind are much higher. So particles can be accelerated to higher energies, and the spectrum can reach TeV energies, as you see here. So this is how the source changes between the inferior and superior conjunctions. Okay, perhaps the most strange of all these gamma ray binaries is PSR 1259. Why? Because we know what is the output in energy of the pulsar that produced the wind. And the radiation we observe in the Earth implies a power that is higher than the power that is injected by the pulsar. So how that is possible? It seems to imply a violation of energy conservation. Well, the idea is that since we have a relativistic wind here, this relativistic wind is confined by the wind of the companion star to some cone like this. And then matter, the relativistic particles moves at relativistic speeds along this cone. They are evacuated through this cone. And when this cone points to you, you see a boosting of the radiation. So in our reference frame, it seems to be a system with a higher power than in the local frame. So it's just a relativistic effect, what we are observing. And this is the whole spectral energy distribution. And you see that there are two different models for different orbital moments. And this band, that is the MEV band, we do not have data. And this data could be very useful to understand how is the transition from this regime to this regime. Likely, COSI, perhaps in a couple of years, will give us some information about this. Okay, I think I am just, oh, Ulises is sleeping. Ulises, it's time to finish? 5 minutes, okay. I will say a few things about novae, and we will continue after the lunch. This is a very bad signal when your chairman is sleeping. Probably the rest of you are just completely. Well, what are these gamma ray novae? These are systems, binary systems again, but they are powered by thermonuclear explosions. So we have two kinds of the systems, symbiotic binaries and classical novae. In the symbiotic binaries, we have the donor star is a red giant. This red giant, you know, is a star that with a very evolved, expanded atmosphere. And then the compact object, the white dwarfs, moves inside this atmosphere, and it accretes from the atmosphere. So from time to time, there is a runaway thermonuclear explosion on the surface of the white dwarfs. In the classical novae, we have a normal star and then accretion through the Roche lobe on the white dwarf. And also we have a thermonuclear explosion, but not so frequently as in this case. So these are called also recurrent novae. Okay. So some of these systems have been detected by the different instruments. Fermi was the first one to detect a novae 15 years ago. This was just a classical novae, V407 Cygni. And here you have the spectrum. So you see that the maximum energy is just scarcely above 10 GeVs. And then several other systems were located, but then recently it was detected by Hess emission from this symbiotic novae, RS Ophiuchi, with TV emission. And I will tell you that after the lunch, because I suspect that most of you are also sleeping. Okay, thank you.
So, for those of you who could resist Gustavo's soft voice, any questions?
Thank you for the talk. I was just curious on the part of, I have two questions. The wind binaries. You said that it's not in every part of the orbit that they emit the gamma rays. In which part of the orbit is the most accelerated parts, or?
Yeah, it depends on the eccentricity and the particular system. But normally, when you are on the periastron, you are very close to the stars. And this means, of course, a lot of radiation for inverse Compton upscattering, but also a lot of absorption. So the interesting aspect is that we expect the highest emission just before the periastron passage and after the periastron passage because of the absorption.
Okay, nice. And the other question is about the gamma ray binaries. Are they the same system as high mass X-ray binaries? Or
They
they are
produce a lot,
different?
they are not the same. They produce, of course, a lot of X-ray emission, but they are not accreting systems. Why? Because the pulsar has this powerful wind that prevents accretion. So the matcha that comes from the star collides with the relativistic wind from the pulsar that is quite young. Because of this, it has such a powerful wind and stops accretion. So there is no accretion. When there is accretion, you have an X-ray binary, and you perhaps will have also a microquasar. So when we come back, I will talk about microquasars.
What is normally the mass of the companion?
It depends,
Of
but
the gamma ray
usually
binaries.
in the gamma ray binaries, it seems to be a BE star. This is a massive star, B star, but the E means that they have also a decretion disk around the star. So the star has an equatorial wind besides the fast wind that is expelled. And this is a very dense wind that perhaps plays some role in the interaction during the periastron passage.
Okay, thank you.
Yeah, regarding my soft voice, there is a reason, because you remember that yesterday I was more animated, but now I have a strong cold. So since I have two talks, one after the other, then I need to take care with my voice, and so I speak softly.
Well, thank you for the insightful lecture. I have a question on the supernova remnant, RXJ, and so on. Are there any models developed in order to explain the ETCA detection? I mean, maybe a second electron population picking out lower frequencies?
Let's see here. So you are asking whether there is an electron population to explain what? Sorry.
The ETCA detection.
The ETCA detection. So this. Well, if you try to fit the entire emission from the source with the same population, no. But when you decompose the source in different pieces, then you can fit the radio data very well, but with different contributions, with different slopes in the spectrum. So it's very complex.
You only have one point data at those frequencies?
No, because fortunately, ATCA also can resolve the supernova remnants. So you need to compare the Hess image with the map of the source. In this just spectral energy distribution, I put just one single point. Right. But you have, for each region, a selection of points with spectrum and all that. Yeah. So this was just the first attempt. You see that here you have Susaku, not Chandra. So this was the first attempt, to try to figure out what's going on, and well, something was wrong. So people were deeper and deeper in this source. There is a funny story about this source, because in the early 2000s, it was claimed by the extinct Kangaroo collaboration, perhaps Ulysses remember, that this source was super proton accelerator with a confidence, a significance in the detection by Kangaroo of 32 sigma. So something extremely bright. But then it was shown that this was contamination by cosmic rays. And that was probably the end of kangaroo. So the moral is be careful when you claim something, be sure about your systematics.
Yes, when kangaroo claimed some things, it was a good indication it was not true.
Yes, yes. You remember, every source they detected was 30-something sigma, so something very suspicious. I remember discussing with Felix Jaronian in Mexico airport very heatedly about this. But please.
Thank you for the lecture. I was wondering, when you were talking about supernova remnants, you said there's the forward shock and also the reverse shock. And I don't know much about supernova, but I know there's the factor 4 of density that changes. I was wondering how the particles see the forward shock and then reverse, like, would it increase and decrease density?
Yes,
Maybe you could comment a little.
I see your point. The forward shock is the one that is sweeping the material. So there is a lot of matter there. So this shock tends to be radiative because the density of matter is very high. When you compress by a factor of 4 that matter, then the temperature rises a lot and Fermi acceleration is not effective. So the reverse shock that moves in a cleaner medium is the most suitable one for particle acceleration.
That would be a diabatic.
Sorry?
It would be a diabatic?
Yes, it would be adiabatic in most cases. Of course, it depends from case to case. But for instance, when you have also a pulsar inside, the pulsar creates a bubble, so it's very easy to have adiabatic shocks in the bubble.
Thank you.
Anyone else? No. So we are back at 2. Thank you.
Thanks.